Today in Capechi's Corner, we're going to have a review on some topics that we have seen so far in this course. We're going to talk about some commonly confused terms and just other ideas that are worth taking a second look at. In number 1 and number 2, we're going to look at some properties. We're going to look at addition and subtraction. So in number 1, if our given statement is 2x plus 7 is equal to 10, and I'm trying to get to 2x is equal to 3, I like to say we'll draw a wall and figure out how did I get from my hypothesis to my conclusion. In this case, we subtracted 7 to either side to get to 2x is equal to 3. Because of this step right here, we actually subtracted. So that's subtraction property of equality. And number 2, the same idea. If I start with 3x minus 4 is equal to 8, and I want to go to 3x is equal to 12. So we want to figure out how do we get from our hypothesis to our conclusion. There's our wall, and what I did to get to 3x by itself is I added 4 to either side, and now I have 3x is equal to 12. So this is considered the addition property of equality because I added to both sides of the equation. In number 3 and number 4, we're now going to compare multiplication property of equality versus division property of equality. So in number 3, same idea. If I'm starting at 3x is equal to 12 is my hypothesis, and I'm concluding x is equal to 4, what did I do to both sides to get there? I divided. So this is going to be division property of equality. If we look at number 4, I have x divided by 8 is equal to 10, and I'm trying to get is x is equal to 80. So what I did is I actually multiplied both sides by 8. And so my reason is going to be multiplication property of equality. The next topics we're going to compare is addition property of equality and angle addition postulate. Students often confuse these two topics when we start working on proofs. So if you look at number 5, I have the measure of angle 1 is equal to the measure of angle 2. That's one equality statement. And then I have the measure of angle 3 is equal to the measure of angle 4. That's another equality statement. Now, because we have two statements that are equal, what I can do is I can add one part from one side and get the measure of angle 1 plus the measure of angle 3 is equal to the measure of angle 2 plus the measure of angle 4. I'm keeping my equations balanced, and what I just did there is I added the parts together. So I have addition property of equality. Now that's different from angle addition postulate. If we look at number 6, I have the measure of angle 1 plus the measure of angle 2 is equal to my bigger angle, measure of angle ABC. That's angle addition postulate. Angle addition postulate. That is two small angles equal a big angle, as opposed to what I did in number 5 when we had two equality statements, and to keep those statements balanced, we added one piece from each side equal to another piece from each side. In number 7, we're going to look at the two different pieces of angle addition postulate. I always say in class when I teach this, I wish these had two different names. Although they are very similar, they are also very different, especially because this always comes up very early in a geometry course. The first part we're going to talk about, part A, is I can say that the measure of angle ABC is equal to the measure of angle 1 plus the measure of angle 2. I like to say two small equal a big. So I have two small angles, which are 1 and 2. When I add them together, they equal the bigger angle, ABC. Now, the second part of angle addition postulate, in example B, is we have a straight angle, and we know that a straight angle is equal to 180 degrees. So in this diagram, I can say the measure of angle 3 plus the measure of angle 4 is equal to 180. So I can use either of these in a proof, and both reasons would be angle addition postulate. In number 8, we're going to again make some comparisons. So in letter A, it says the measure of angle 1 plus the measure of angle 2 is equal to 180. That's what we just looked at. So this reason is angle addition postulate. Angle addition postulate. When I have a straight angle and I have two angles and I add them together, I know they equal 180 because of angle addition postulate. In letter B, I have angle 3 and angle 4 are supplementary angles. So because of that, I can say the measure of angle 3 plus the measure of angle 4 is equal to 180. Now, why can I say that? Because I told you that the angles are supplementary. So the reason for this step right here, I add them together equal 180, is definition of supplementary angles. Now, looking at our last sample there, letter C, we have the measure of angle ABC is equal to 180. We have a diagram here. We don't really see this a lot in a proof, but students do get this confused. If I know that angle ABC is a straight angle, because when I look at it, it's a line. So because of that, I can say that the measure of angle ABC is equal to 180. The reason I can say that is because of definition of a straight angle. If I read the definition of the straight angle, it says it's an angle with measure of 180 degrees, which is what I have. Now notice in letter C, I didn't add anything together like I did in letter A. And I can't say anything about supplementary angles because, like in letter B, it says that the angles are supplementary. I don't have that information in letter C. The only thing I can say in C is that I know because of that line is there that that measure of that angle, angle ABC, is 180 degrees because of the definition of a straight angle. In example number 9, we're going to look at vertical angles. In letter A, I'm just telling you that angle 1 and angle 2 are vertical angles. And the reason I can say that is because of definition of vertical angles. And I'll read to you that definition. The definition of vertical angles say, two angles whose sides form two pairs of opposite rays. If I look at letter B, I'm saying angle 1 is congruent to angle 2, which is saying something very different than we said in letter A. Angle 1 is congruent to angle 2 because they are vertical angles, so we need to use that theorem. Vertical angles are congruent. Now notice in letter A, when I say 1 and 2 are vertical angles, all I'm doing is identifying them almost like a vocabulary term. 1 and 2 are vertical angles. I'm not saying anything about congruent. In part B, when I'm talking about congruency, I'm talking about the theorem that states vertical angles are congruent. In number 10, we're just working on some notation. It's always a good reminder to do this every now and then. So if I'm looking at number 10, I have angle ABC and angle DEF are both equal to 40. So I can say that those angles are equal because they're both equal to 40. When I do that, I have to put that M in front because I have an equal sign. I can also say the measure of angle ABC is equal to 40 and the measure of angle DEF is equal to 40. So again, whenever I have that equal sign, I'm going to use the M in front. This is different from when I'm talking about congruency. Talking about congruency, I'm not going to have that M in front. I'm simply going to state angle ABC is congruent to angle DEF. Number 11, we have a similar situation. We're going to work with notation, this time with segments. So I can see in my diagram that segment AB has a value of 5, and so does segment ST. So I can state that AB is equal to ST. Notice because I have an equal sign, I don't have that segment bar on top. I can also say AB is equal to 5 and ST is equal to 5. Again, because I have that equal sign, I do not have a segment bar on top. That's going to be different when I'm talking about congruency. When I'm talking about congruency, I am going to have that segment bar on top of each of my segments. Two other commonly confused topics in the beginning of a geometry course are two algebra properties. We have addition property and we have a substitution property, which often get confused. So let's look at number 12. We looked at this example earlier in our video today. I have two equality statements. The measure of angle 1 is equal to the measure of angle 3, and I have the measure of angle 2 is also equal to the measure of angle 4. So what I can do, because they're two equality statements, to keep a new statement balanced, I can say 1 and 2 together are equal, and 3 and 4 together. When I add them together, they're equal. That's considered addition property of equality. Addition property of equality. Now in letter B, we're going to talk about substitution. I know, looking at my diagrams, that I have two small angles equal a big angle. So in number 1, I have the measure of angle ABD is equal to the measure of angle 1 plus the measure of angle 2. And I also have the measure of angle EFH is equal to the measure of angle 3 plus the measure of angle 4. Now, if I was originally given, or at some point during my proof, I'm given that those two big angles are equal, then I can state that the measure of angle 1 plus the measure of angle 2 is equal to the measure of angle 3 and 4, because in my previous statement, I have broken those pieces apart. So in combining 1 and 2 together, I have substituted, I've moved things around, so my reason is going to be substitution, property of equality. The last topic we're going to look at today is perpendicular lines. Now, with perpendicular lines, we have one definition and we have three theorems. So sometimes it's difficult to decide which one to use in a proof. Letter A is talking about the definition of perpendicular lines. And in looking at our diagram, if I tell you that the measure of angle 1 is 90, or measure of angle 2 is equal to 90, or if I tell you that angle 2 is a right angle or angle 1 is a right angle, we know we're talking about definition of perpendicular lines. So when we're talking about the definition, you're going to see one of two things. You're either going to see 90 degrees mentioned, or you're going to see the fact that it's a right angle. In letter B, this theorem says if two lines are perpendicular, then they form congruent adjacent angles. So an example is if I tell you that line AD is perpendicular to ray BC, you can then conclude that those angles, angle 1 and angle 2, are congruent. So again, the important thing, the hypothesis there is that the lines are perpendicular, and the conclusion is that the angles are congruent. They're also adjacent, as we can see from the diagram. Letter C, this theorem is actually the converse of what we saw in letter B. It says if two lines form congruent adjacent angles, then the lines are perpendicular. So it's the opposite. If I tell you the angles 1 and 2 are congruent, you can see from the diagram that they're also adjacent, then you can conclude that the lines are perpendicular. So again, we have to decide what are we given. Our hypothesis is that the angles are adjacent and they're also congruent, and my conclusion is that the lines are perpendicular. And in our last theorem discussing perpendicular lines, this one states, if the exterior sides of two adjacent acute angles are perpendicular, then the angles are complementary. So if you look at our diagram, the exterior sides, which are the outsides, are ray OA and ray OC. If we are told that they're perpendicular, then we can conclude that angle AOB and angle BOC are complementary angles. So in this theorem, if those rays are set up and we know that they're perpendicular, then we can conclude that the angles that are formed are complementary.